Hello and welcome to video 4 of linear ODEs. Still getting used to making these videos, so you have to excuse the poor quality. So this particular lecture is about linear ODEs, and in particular those that have constant coefficients and are homogeneous. Okay, so this is a particular case where we can find the solutions even of higher order differential equations. So we've seen in the previous lecture that when an ODE is linear and homogeneous, we can combine solutions together using the superposition principle, that any linear combination of solutions is a solution. So that means we can find the general solution just by finding a set of linearly independent elementary solutions to the differential equation. And there is no general method except for finding those elementary solutions, except where the differential equation has constant coefficients, and that's what we're going to talk about today. So the first thing is to see what kind of differential equation we're talking about. So if we look at the examples here, so is this a linear ordinary differential equation with constant coefficients, and is it homogeneous? So the answer to this first one is no, this is non-linear, okay, because of this squared term. So that's not the right kind of differential equation, non-linear. Looking at this second one, this is linear now, but if we look at the coefficient of x here, we see that it depends on t, so it's not constant. So this is not constant coefficient. And moving on to the third example, this one is now linear, and it has coefficients 4 and 1, and those are both constant, so it is linear with constant coefficients, but the right hand side is not 0. Okay, so that means that this is not homogeneous. And that leaves us finally with this ODE at the bottom here. This is linear, and it has constant coefficients 1 and 4, and the right hand side is 0, so it's homogeneous. Okay, so this is linear, constant coefficients, and homogeneous. And this is the kind of differential equation that we're going to look at solving in this video and in some of the subsequent videos. So first, let's review the general procedure here. So when given an ordinary differential equation, the first thing we want to do is classify that equation, which is what we did on the previous slide. So if the equation is linear and has constant coefficients and is homogeneous, then we can use the rest of this procedure. So the next step is to use the exponential ansatz. Okay, and we'll see what that is on the next slide, and that gives us the characteristic equation from which we find the elementary solutions, which then we can then use to write down the general solution. Okay, so if we skip over to the next slide here, what we can see is this is the example we're going to solve. So we have differential equation d2x by dt squared minus 4x equals 0, and with initial conditions x of 0 equals 1 and x dot of 0 equals 2. Okay, so let's work through this example carefully over the next few slides. So the equation was d2x by dt squared minus 4x equals 0, and we're going to use the exponential ansatz. What does that mean? It means we're going to substitute x equals e to the lambda t. So for this class of equations, there will always be at least one solution of this form for some value of lambda. So we can substitute this in and then try to figure out what lambda is afterwards. So the next step, if we want to substitute this in for x, we see that the differential equation has x, but it also has d2x by dt squared. So we're going to need to figure out what d2x by dt squared is. And to get there, we differentiate this equation twice. So differentiating once, what we find is dx by dt equals lambda e to the lambda t. Okay, so when we differentiate the exponential function, it goes to itself, but we'll get a factor of lambda out. And if we differentiate again, then the same thing will happen. So d2x by dt squared equals lambda squared e to the lambda t. So now we have d2x by dt squared and x from our ansatz, that x equals e to the lambda t, and we can substitute those into the differential equation to see where that takes us. So now d2x by dt squared becomes lambda squared e to the lambda t, and x becomes e to the lambda t, equals 0. Now we see that both terms on the left here have a factor of e to the lambda t, so we can factorise this, and we'll get lambda squared minus 4 times e to the lambda t equals 0. So now one of these two things, or at least one of these two things, has to be 0. E to the lambda t is never 0, so that tells us we can divide by e to the lambda t here, and we can get lambda squared minus 4 equals 0, which then leads to our two possible values for lambda. So lambda equals plus or minus 2. So what we've seen here is that we tried a solution of the form x equals e to the lambda t, and we substitute that into the differential equation, and working through we find that that trial solution, e to the lambda t, will work provided lambda is one of these two values, either plus 2 or minus 2. Okay, so that tells us that there are two possible solutions, and so one is x equals e to the 2t, and the other is x equals e to the minus 2t. So these two possible solutions now we can combine using the linearity of the differential equation. So we pop over to the next slide. So what we found was that we've got one solution, x1, which is equal to e to the 2t. We have another solution, x2, which is equal to e to the minus 2t. But since this is a linear homogeneous ODE, we can make the general solution by combining those two. So we get x equals a e to the 2t plus b e to the minus 2t. And this now, which has two integration constants, a and b, which is what we need for a second order ODE. And this now gives us the general solution for x. Okay, so on the next slide here, we're going to work down and see what the constants a and b would have to be given the initial conditions that we started with. So the solution, the general solution that we have is x equals a e to the 2t plus b e to the minus 2t. And we have the initial conditions x of 0 equals 1 and x dot of 0 equals 2. So if we substitute those in here, so to use the condition x of 0 equals 1, we replace x with 1 and t with 0 in this equation. So we get 1 equals a e to the 0 plus b e to the 0. E to the 0 is just 1. So this gives us the equation a plus b equals 1. And then substituting the other solution in here, we need to figure out, so x dot means dx by dt, so we'll have to differentiate our general solution before we can substitute into it. So dx by dt equals, so differentiating a e to the 2t will give us 2a e to the 2t, and differentiating b e to the minus 2t will give us minus 2b e to the minus 2t. And now again we can substitute, so the initial condition says that dx by dt is 2 when t is 0. So we place dx by dt here with 2, and we'll place t with 0. So e to the 0 is 1 again, so this gives us 2 equals 2a minus 2b. And dividing through by 2 there, that then gives us that a minus b equals 1. And we can solve this pair of simultaneous equations now for a and b. And what we'll find is that a equals 1 and b equals 0. So that gives us finally the particular solution for these initial conditions is x equals e to the 2t. So this is replacing a here with 1 and b with 0. So that's the particular solution to this particular initial value problem with these initial conditions. And what we'll find though, in general though, with different initial conditions we can get different solutions for the same differential equation. And if we pop on to the next slide, we can have a quick plot of what these solutions look like. So the original differential equation was d2x by dt squared minus 4x equals 0. And we saw that there were two fundamental solutions. One is e to the 2t, which looks like this red curve increasing. And the other is e to the minus 2t, which looks like this blue curve, which decreases and goes exponentially to 0. So one goes exponentially to infinity, and the other goes exponentially to 0. And we found in our case that we had the solution that was the red curve, e to the 2t. So our solution will go exponentially towards infinity. But for different initial conditions, we could have had other possible solutions. So now, having worked through all of that, let's take another example. So we'll just remind ourselves what the procedure was. So first we had to classify the ODE, and we had to see whether it matches the particular form we want, which needs to be linear with constant coefficients and homogeneous. Then we used the exponential answer. So this was x equals e to the lambda t, and that led us to the characteristic equation, which was lambda squared minus 4 equals 0, with the roots being plus or minus 2, so that gives us the elementary solutions, e to the 2t and e to the minus 2t. And finally we get to the general solution, a e to the 2t plus b e to the minus 2t. Okay, so that's the method, and that's how it works through in this example. So let's try one more complicated example at the end here. So we have here a differential equation is d2x by dt squared minus 5 dx by dt plus 6x equals 0. So we'll start with x equals e to the lambda t, and dx by dt is lambda e to the lambda t, d2x by dt squared is lambda squared. Substituting those in, what we will get is lambda squared e to the lambda t minus 5 lambda e to the lambda t plus 6 e to the lambda t equals 0. Dividing out the e to the lambda t, we will get lambda squared minus 5 lambda plus 6 equals 0. And this is something that we can factorize. So factorizing this, we will have lambda minus 2 times lambda minus 3 equals 0. And you can check if we multiply that out, we'll get lambda squared minus 5 lambda plus 6. So that gives us two possible values. Lambda is 2 or lambda is 3. So lambda equals 2 or 3. And that then gives us the two solutions, e to the 2t and e to the 3t. And the general solution is going to be x equals a e to the 2t plus b e to the 3t. So that's another example, just worked through more quickly there. And coming back to the method once more, what we see, we classify, use the exponential ansatz, find the characteristic equation, which is always a polynomial, which we can solve using each of the quadratic formula, find the elementary solutions, and then build the general solution. Okay, and this is how we solve any ODE which is linear and homogeneous and has constant coefficients. So finally, here are some exercises for you to work through. So see if you can find the general solution for each of these ODEs.